As I mentioned before, the Java FutureTask is something that's a little hard to understand in isolation, so I'm going to give you an example of how to use it, and we're going to use it in order to design something called a Memoizer. And a Memoizer is not a mispronunciation of the word memorizer. It's actually something called a Memoizer, and it's an abstraction we'll talk about in a second. And we're going to use this particular Memoizer to cache the results of long-running function calls and then return those cache results for the same input. So it's basically a cache. So Memoization, which you can read about here if you go to this Wikipedia link, is an optimization technique that's commonly used to speed programs up. And what it does is it caches the results of expensive function calls. So let's take a look at an example of such a thing. So if you recall the Concurrent Hashmap class, Concurrent Hashmap has a method called compute if absent. And that's a good example of a Memoizer. So here's kind of how this would work. If a key that's passed in doesn't already exist in the cache, then invoke some potentially long-running function, which is also passed as a parameter, that's associated with the key, and then store the resulting value in some kind of data structure based on the key. And then return the value that's associated with the key. So, of course, if the key already exists, then we just return the key. Now, when the same input occurs again, the cached results, actually the value, not the key, the cached results are returned. So you can see here, if you call compute if absent and the key already exists in the cache, then return the cached value that's associated with the key. So that's basically the way it works. The first time in, it'll go ahead and perform the long-running function, take the result, store it in the map via the key, and then return the value. All subsequent times, if you look something up that already exists, it'll just return the value, which is what a cache does, of course. And so that's essentially what a Memoizer is used for. But the key point here is that there's a function that's called in order to compute the result. So we're going to define ourselves a class called Memoizer that is going to return the value produced by applying this potentially long-running function to a key. So there's a class we have called Memoizer, and it's going to extend the function class, a function interface. This particular way of doing things is heavily based on some discussions in a classic book by Brian Getz and some of his colleagues called Java Concurrency in Practice. And it's a great book. I highly recommend that you take a look at it. You can learn more about it here. Java Concurrency in Practice, or jcip.net. So as I mentioned before, if there's a value that's already computed for a key, it's just returned rather than applying the function to recompute it. That's what's being cached, is that value. By implementing the functional interface, a Memoizer can be used whenever a function is expected. And this is going to turn out to be a really cool thing, and you'll see how we get to use that. So you can basically transparently add memoization to your programs in lieu of just using a function that gets called every time. And that's really, really neat. Now, the way we're going to do this under the hood is we're going to use a concurrent hash map to minimize synchronization overhead. And you all know concurrent hash map, and you'll see how that gets applied here. Now, the thing that's nice about concurrent hash map is that different lock guards are used for each hash bin. This is something that's relatively recent, probably in the last 10 years or so. So it's relatively recent in the scope of Java. And so each of the elements in the hash table is used as a compare and swap wait-free lock in order to be able to minimize contention for concurrent access of the contents of the hash table. So basically, you can think of every entry here has its own separate lock. So that greatly speeds things up. If you need a refresher on what concurrent hash map does, go back and take a look at the videos that talk about that. Yeah. That's right. It's interesting. So the question was, what are the hash bins that are called here? What are they implemented as? And the answer is, it depends on what version of Java you're using. Earlier versions of Java used linked lists that came off of each of these things, which is kind of the classic way of doing things. Later versions of Java, and I think this is actually described in this link here, are very clever in that they adaptively replace a linked list with a balanced binary tree if they notice that there's a lot of elements starting to hash to the same location. Which, if you think about it, if you remember your data structures course from back in the day, one of the downsides with a classic linked list implementation of a hash table is that under worst case assumptions, you can end up with basically taking linear time to do adds and removes and finds, which is defeating the purpose of using a hash table. But if you use a balanced binary tree, then it takes no more than log n time to do that. Now, you might ask the other question, which is sort of an obvious one. Why don't they just use a balanced binary tree all the time? And the reason for that is that maintaining a balanced binary tree costs you something relative to maintaining a linked list. Linked lists are super duper easy to implement. And as long as you don't have a lot of keys hashing to the same hash bin or bucket or whatever we want to call it, then you're probably better off using a linked list. So that's why it's adaptive. It keeps track of whether or not things are overly hashing to the same location. And when it passes a certain threshold, it'll convert that into a balanced binary tree. So pretty cool stuff. Just for sake of comparison, remember synchronized map. We talked about synchronized map at various points. That just has a single lock that guards all the entries in the hash table, and therefore contention is higher because there's only one lock that's being used. Okay, so popping back out of concurrent hash map land for a moment, compute value uses FutureTask to ensure a function runs only when the key is first added to the cache. This is very, very, very important, and this is kind of the heart of the whole thing. And only one computation will occur even if multiple threads simultaneously call compute value for the same key. And I'll kind of describe the circumstances under which that could occur. But assuming that you had a whole bunch of threads and they were all coming in with the same key that had not been seen before at exactly the same time, we're going to use FutureTask to make sure we only call the function one time. And I'll also explain why that's important. Okay, so that's a quick overview of the Memoizer as a data structure, as an abstraction, as an abstract data type. And then in the next lesson, we'll talk about how to implement this using FutureTask.